Welcome, curious minds, to the deep dive. Today, we're plunging into a question that has, well, it's haunted and inspired humanity probably since we first looked up at the stars. Are we alone in the universe?
It's such a fundamental question, isn't it?
Exactly. And for millennia, this was, purely the realm of philosophers, poets, maybe dreamers. It was basically science fiction. But what's truly astonishing, I think, is how rapidly this really profound existential inquiry has transformed into a vibrant, rigorous scientific quest. It's moved from just speculative thought to actual measurable data.
Yeah, the shift is incredible. We're actually looking for evidence now, not just wondering.
Right. So our mission on this deep dive is to explore the cutting edge of this scientific search for extraterrestrial life. We're drawing directly from, well, a stack of fascinating articles, research papers, and of course, your own expertise on the topic.
Happy to be here and dive in.
Great. So we're going to embark on a journey that starts, maybe surprisingly, incredibly close to home, right here in our cosmic backyard.
Your own solar system, yeah.
Then we'll zoom light years out to the sheer vastness of the Milky Way.
Yeah.
We'll definitely confront a deeply unsettling cosmic paradox.
Ah, the big one.
The big one. And then, crucially, we'll look at the revolutionary, really cutting-edge tools that are extending humanity's observational and exploratory reach further than ever before.
It's an exciting time for that.
Absolutely.
Yeah.
We're essentially tackling this grand question on two major fronts, right? There's the direct robotic exploration. Think of the incredible missions currently unfolding on Mars.
Rovers on the ground, yeah.
And then there's the remote observation, peering through these incredibly powerful telescopes at distant stars and the worlds orbiting them.
Looking for clues from afar.
Precisely. So our conversation today is going to revolve around, let's say, three core pillars. The really tantalizing story of Mars, the grand probabilistic framework offered by the Drake equation,
Always fascinating.
and the chilling, profound implications of what we call the Fermi Paradox.
And, by the end of this deep dive, you, our listener, should have a really robust and, I hope, nuanced understanding of the current state of astrobiology.
That's the goal.
Yeah, we really aim to equip you with insight into the major questions scientists are grappling with right now, the methodologies they're actually employing, and the truly exciting possibilities that lie ahead.
Possibilities, and maybe some unsettling thoughts, too.
Definitely both. What's truly fascinating here, and something we'll try to emphasize, is how these seemingly disparate fields, everything from the granular details of planetary geology and atmospheric chemistry to the grand sweep of astrophysics and even evolutionary biology, how they all converge with increasing precision on this single, maybe epoch-defining question.
It all comes together.
It really does. We're going to try and connect those dots for you, giving you not just, a list of facts, but hopefully that crucial shortcut to being truly well-informed. And, well, maybe sparking some genuine aha moments about our own unique place in the cosmos.
I like the sound of aha moments. Okay, so before we dive into potential cosmic neighbors, let's maybe zoom out a bit to the very fabric of existence itself.
Foundational stuff.
Exactly. Because to truly understand where life might arise and, importantly, thrive, we first need to grasp the fundamental physics that literally shapes worlds and determines their potential for habitability.
Makes sense.
And at the heart of that, defining every orbit, every galactic structure, is gravity. But maybe not gravity as we usually think about it.
Yeah.
It's a force, maybe not a force, far more profound than our everyday experience suggests.
Right, moving beyond Newton.
That's it. Let's get into that. Okay, so gravity. Even for those of us, familiar with the basics, it's really easy to fall back on that intuitive, kind of Newtonian view of gravity. The apple falling from the tree, the pull of the earth, what keeps our feet on the ground.
The force that pulls things together, that's the standard picture.
It is. And that classical understanding, where gravity is this invisible force instantaneously pulling objects toward each other across space, it's incredibly useful for everyday calculations, right? For launching rockets, for a lot of engineering.
Works perfectly well for most things we do, yeah.
But, and here's the shift, as Albert Einstein so profoundly demonstrated with his theory of general relativity, that picture, while useful, is ultimately, well, insufficient. Especially when we're trying to understand the cosmos on a grand, fundamental scale.
Like how planets orbit stars, or how galaxies hold together.
Exactly. When we're talking about the intricate dance of planets around stars, or the very structure of galaxies, Newton's idea doesn't quite cut it. You can say Newton described what gravity does brilliantly, but Einstein explained what gravity is.
A deeper level of
A
understanding.
much deeper level. And here's where it gets really interesting, I think, and where our understanding of space and time takes this radical turn. Einstein's general relativity proposes that gravity isn't actually a force pulling in the traditional sense at all.
Okay, so if it's not a pull, what is it?
It's a manifestation of the curvature of space-time itself. Space and time woven together into a kind of fabric.
Space-time, right?
To visualize this, and this is the classic analogy, but it really helps reshape our intuition. Imagine the universe not as an empty stage, but as this vast, incredibly flexible fabric, like a flat, taut trampoline stretched infinitely across all dimensions.
Okay, got the trampoline in mind.
This trampoline represents the four-dimensional fabric of space-time. Now, if you were to place something heavy, let's say a bowling ball right in the center of that trampoline, what happens?
It sinks down, makes a dip, the fabric curves around it.
Exactly. The surface doesn't remain flat. It curves and sags under the weight, or rather the mass, of the bowling ball, creating an indentation. That curvature, that indentation in the fabric of space-time is gravity.
So mass tells space-time how to curve.
You got it. A massive object, like a star, or even a planet, isn't pulling things towards it in the Newtonian sense. It's warping the space-time around it. So then if you roll a smaller object, like a marble, across that trampoline near the bowling ball, what path does it take?
It doesn't go straight, right? It curves towards the bowling ball, follows the dip.
Precisely. It doesn't get pulled directly into the bowling ball by some invisible string. Instead, it simply follows the curve in the fabric created by the bowling ball's mass. It's taking what physicists call a geodesic, which is essentially the straightest possible path it can take. But that path is now through a profoundly curved medium, through curved space-time itself.
Okay, so it's just following the contours of space-time.
That's the essence of an orbit. It's not some mystical pull across empty space. It's an object following the geometry, the shape of space and time that has been distorted by a larger mass. It's an incredibly elegant and, frankly, mind-bending idea, but it underpins all of modern astrophysics.
It really is a beautiful concept. And this foundational idea, this picture of gravity as geometry, is absolutely vital for astrobiology. It dictates, well, pretty much everything relevant to finding life.
How so? Connect that for us.
Well, if we connect this back to the bigger picture, understanding gravity as the geometry of the universe is really our first step in figuring out where other marbles like Earth might even exist on this cosmic trampoline.
Okay.
This isn't just some abstract physical concept. It determines where planets can actually form in the first place within those swirling disks of gas and dust around young stars. It governs how they maintain stable, long-term orbits around their parent stars.
Stability seems key for life.
Absolutely key. And crucially, this gravitational geometry defines the very structure and long-term stability of entire solar systems. Think about it when we talk about life, especially life as we know it. We critically need liquid water. It's the solvent, the medium.
The basis for everything we understand, yeah.
Exactly. And for liquid water to exist stably on a planet's surface, that planet needs to be in a very specific orbital region around its star. Region where the temperatures, dictated by the star's energy output and the planet's distance, are neither too hot for water to just boil away into space, nor too cold for it to remain perpetually frozen solid.
The Goldilocks zone.
That's the one, the Goldilocks zone, or, more formally, the habitable zone. It's that just right sweet spot, where a star's energy output and its gravitational influence, which dictates the orbit, combine to create conditions potentially suitable for liquid surface water.
And gravity keeps it there.
Gravity ensures it stays there. Without a stable orbit dictated by this cosmic geometry, a planet could easily be flung out of its system into the cold darkness of interstellar space, or spiral into its star in a fiery death. Neither is good for life.
Definitely not.
Life, as we imagine it, likely needs millions, or more likely billions, of years of relative stability to emerge, evolve, and become complex. And that stability is fundamentally provided by gravity maintaining those orbits within the habitable zone. So understanding gravity is step one in finding potentially habitable worlds.
That's a really profound framework for understanding the possibilities out there. Okay, with that cosmic stage now, hopefully a bit clearer in our minds, this idea of curved space-time and stable orbits, let's bring it back closer to home. Let's zoom back into our own cosmic backyard and explore the most scrutinized marble in our solar system, the one that has truly captured our imaginations for centuries. Mars.
Ah, yes, the red planet, always compelling.
Mars. It's been the subject of, well, intense human fascination and scientific inquiry for literally centuries, hasn't it?
Yeah,
And for good reason.
definitely. From those early telescopic observations that sparked wild tales of canals and dying civilizations.
Goals, canals, right.
Exactly, all the way to the present day, where we have this amazing fleet of sophisticated robotic explorers, orbiters, landers, rovers, sending back incredible data. Our red neighbor just continues to intrigue.
And today, when we look at it, or at least the pictures it sends back, it's a world that, on the surface, looks incredibly harsh. You picture this frigid, desolate landscape, basically a deeply rusted desert.
You're red, yeah.
Battered by a paper-thin atmosphere. Where does it only about 1% the density of Earth's?
Roughly, yes. Very little protection.
And constantly bombarded by sterilizing solar and cosmic radiation hitting the surface. It seems like a truly inhospitable place for life, as we understand it. At least life on the surface today.
Surface conditions are brutal, no question.
But, and this is the crucial but, what's truly astonishing, and what our robotic emissaries, these rovers and orbiters, have unequivocally shown us, is how dramatically this picture changes when we look deep into Mars's ancient past.
Billions of years ago.
Exactly. The evidence sent back by this whole fleet of machines paints a vivid, almost unbelievable picture of a planet that was once dramatically, almost unrecognizably different.
Warmer, wetter, completely different environment.
The echoes of a profoundly watery past on Mars aren't just speculation anymore, are they? They seem to be overwhelming geological certainties now.
Oh, absolutely. The geological evidence is compelling. Billions of years ago, the red planet was, without a doubt, a warmer, wetter planet. A world that could have hosted extensive bodies of liquid water lakes, maybe even shallow seas for prolonged periods.
And we see the remnants.
We see the remnants everywhere. Just think about the Curiosity rover. It's been tirelessly exploring Gale Crater for, what, over a decade now?
Incredible mission longevity.
It really is. And its findings are remarkable. It has literally driven through the remnants of what were once vast ancient lake beds. It found these finely layered mudstones.
Like you'd find at the bottom of a lake on Earth.
Precisely, definitive proof that standing water deep enough and calm enough to form these fine sedimentary deposits existed there for thousands, maybe even millions of years. This wasn't just a flash flood, it was sustained bodies of water, potentially conducive to the slow processes of sedimentation and maybe life. Curiosity also found evidence of specific minerals, like hematite spherules, they nicknamed them blueberries, which typically form here on Earth in the presence of water. Little geological clues scattered around.
And then there's Perseverance, the newer rover.
Right, Perseverance. Our newest robotic emissary on the surface landed in 2021. And its landing site was chosen very specifically, Jezero Crater.
Why Jezero?
Because scientists using orbital data identified Jezero Crater as the location of a spectacular ancient river delta. You can see the fan-shaped structure from orbit. It's a geological feature unequivocally formed by a river flowing into a lake, depositing vast amounts of sediment over time.
Just like the Mississippi Delta, but on Mars.
Exactly the same kind of process. Its primary mission is to explore these incredibly rich sedimentary deposits. Now, why focus on those? Because sedimentary environments, especially those formed in the relatively calm waters of ancient lakes or river deltas, are considered absolute prime locations on Mars for preserving any delicate signs of past life, if it existed.
Like crapping fossils.
Sort of, but think smaller, much smaller. The fine-grained sediments act like a natural time capsule, potentially protecting fragile organic molecules and other subtle biosignatures from the harsh surface environment over billions of years. So the geological evidence is now, I'd say, overwhelming. Liquid water, the very solvent of life, was once abundant and persistent on the Martian surface.
So it's not really a question of if Mars had water anymore.
No, the debate has moved on. It's now about when, how much, for how long, and critically, was it actually habitable in the sense of having all the necessary ingredients and conditions for life?
Which leads us right to the next big question. Did life actually take hold?
That's the multi-billion-dollar question. And that leads us directly to the current critical phase in the Mars exploration program, the active hunt for biosignatures.
Okay, biosignatures. What exactly are we talking about there? You mentioned not fossils.
Right. It's really important to clarify that when scientists talk about biosignatures on Mars, we're generally not talking about finding fossilized bones or, the remains of large, complex creatures.
No little green men.
Definitely no little green men. That's simply not what our current rovers are equipped to find, nor is it what we realistically expect based on Mars's history. Instead, biosignatures are the the subtle chemical, isotopic, or mineralogical evidence that points towards past biological activity.
So more like chemical clues left behind.
Exactly. Think of them as the tiny, microscopic clues left behind by microbial life, much like the evidence of ancient bacteria, like stromatolites, or specific chemical ratios that we find in Earth's oldest rocks from billions of years ago.
Okay, so what have the rovers found so far in that department? Anything concrete?
Well, the latest findings from both Curiosity and Perseverance have been incredibly tantalizing, really fascinating stuff. But, and this is a crucial scientific distinction, still ultimately inconclusive.
The caveat.
Always the caveat in science. For instance, both rovers have definitively detected a variety of complex organic molecules, specifically carbon-based molecules, which are, the fundamental building blocks of life as we know it,
Found where?
preserved within ancient Martian rocks, especially those mudstones in Gale Crater that Curiosity looked at. Curiosity found things like thiophenes, benzene, toluene, and small carbon chains, compounds that can be components of biological material.
So building blocks were there.
Their presence confirms that, yes, the raw ingredients, the fundamental chemical building blocks required for life, were indeed present on ancient Mars. That's a huge finding in itself. However,
Here come.
it's absolutely crucial for us and for you listening to understand that organic, in a chemical sense, doesn't automatically mean biological.
Right. Chemistry versus life.
Precisely. These complex carbon molecules could absolutely have been produced by purely geological processes. Think about reactions happening in hydrothermal vents, maybe deep underground, involving water and rock. Or they could even have been delivered to Mars constantly over billions of years by carbon-rich meteorites impacting the surface.
So distinguishing the source is the challenge.
That's the core challenge. Distinguishing between abiotic, non-biological, and biological origins often requires very specific, detailed analyses, like looking at the ratios of different isotopes of carbon or the specific structures of the molecules, like chirality or handedness. And those analyses are extremely difficult, maybe impossible, to perform definitively with the kind of miniaturized instruments we can realistically mount on a rover millions of miles away.
Okay, so organic molecules, present, but origin unknown. What else?
Then there's the intriguing and honestly truly baffling mystery of methane plumes.
Methane. Like cow burps on Earth.
Well, yes, but probably not from Martian cows. For years now, orbiting spacecraft and even Curiosity on the surface have detected transient seasonal plumes of methane gas in the very thin Martian atmosphere. These plumes seem to appear, then disappear, and their concentration seems to vary with the Martian seasons and maybe even the time of day.
Why is that exciting?
It's incredibly exciting because here on Earth, something like over 90% of the methane in our atmosphere is produced by living organisms, primarily microbes called methanogens, but also through other biological processes and even geological activity influenced by life.
So on Earth, methane often equals life.
It's a strong indicator, yes. The sporadic and unpredictable nature of these Martian plumes makes their origin a truly compelling mystery that scientists are still actively investigating. Does it indicate pockets of active subsurface biology, microbes perhaps releasing methane periodically?
That would be huge.
Monumental. Or is it produced by purely geological reactions? For example, a process called serpentinization, where certain types of rocks react with water deep underground, can release methane. Or maybe it's ancient methane that was trapped in ice crystals called clathrates beneath the surface, and it's being released sporadically due to changes in temperature or pressure.
So again, geology or biology?
Exactly. The jury is still very much out. We need more data, more observations, ideally detecting a plume directly and analyzing its isotopic composition to try and pin down the source. It remains a top priority mystery.
It sounds like there are hints, but nothing solid yet.
Hints, tantalizing clues, converging lines of evidence, but no smoking gun. And finally, building on that idea of subsurface activity, we have strong evidence of potential subsurface niches for life.
Niches, like hideouts.
Sort of. While the surface of Mars today is undeniably inhospitable, that brutal environment scourged by radiation, extreme temperature swings, dryness,
Yes, sounds awful.
conditions just a few meters underground may be far more favorable for life. Orbiters circling Mars, using radar and other instruments, have confirmed the existence of vast deposits of water ice buried beneath the surface, not just at the poles, but even at surprisingly low latitudes closer to the equator.
Frozen water underground.
Lots of it. And this immediately raises a fascinating possibility. It is entirely conceivable that microbial life, perhaps similar to Earth's incredible extremophiles, those organisms that thrive in places we once thought impossible, like deep-sea hydrothermal vents without sunlight, or miles deep within solid rock, or in super salty water.
Life finds a way, kind of thing.
That's the idea. Perhaps similar microbes could persist or even thrive today in these shielded, potentially water-rich subterranean environments on Mars. Deep beneath the surface, they would be protected from the harsh surface radiation and the extreme temperature fluctuations.
What would they eat?
Good question. They might harness chemical energy from reactions between water and the surrounding rocks, much like chemosynthetic organisms do in Earth's deep subsurface or at hydrothermal vents. This potential for a hidden subterranean Martian biosphere is a really powerful driver for future exploration missions that might need to drill down to access these environments.
That's a really comprehensive picture of the current state of play on Mars. It really feels like we're circling something, doesn't it? All these tantalizing hints, the ancient water, the organics, the methane, the subsurface ice.
It definitely feels like we're closing in on answering the big questions about Mars's past and maybe even present habitability.
So for all that tantalizing evidence, it still sounds like we're left with more questions than definitive answers. Is it frustrating for the scientists involved, being so close, yet still unable to definitively say, yes, this is proof of life, or no, it's definitely just geology?
Oh, I think frustrating is probably an understatement for many. It's incredibly challenging, and yes, frustrating, to be potentially on the cusp of such a monumental discovery, arguably the biggest scientific discovery in human history, and to have the evidence be so suggestive, yet stubbornly ambiguous.
What's the single biggest hurdle there? Why can't the rovers just give us a clear yes or no?
That's an excellent question, and it perfectly encapsulates the challenge. The biggest hurdle, fundamentally, is the inherent limitations of doing complex science remotely via robot on another planet. It's about in situ analysis.
Doing the tests right there on Mars.
Exactly. Doing experiments on another planet with instruments that are, by necessity, much smaller, less powerful, consume less energy, and are generally more constrained than the state-of-the-art equipment we have in sophisticated laboratories right here on Earth.
Makes sense. They have to survive launch, landing, the Martian environment.
Precisely. These rover instruments, the cameras, the spectrometers, the drills, the lasers, they are absolute marvels of engineering, miracles of miniaturization. But they simply cannot perform the full suite of tests needed for definitive proof of life. They can't easily do the ultra-precise isotopic analysis needed to distinguish biological carbon from geological carbon, for instance. They can't perform the kind of advanced microscopy needed to identify potential microfossils unequivocally. They can't run the complex organic chemistry experiments that could definitively determine if those organic molecules have the specific structures, like a preference for left-handed or right-handed amino acids that are characteristic of life as we know it.
So we need better labs.
We need our labs. We need the samples here. Which brings us to the ultimate goal, really the critical next step, and arguably the most ambitious robotic mission ever conceived in our entire quest to explore Mars. The Mars Sample Return Mission.
Oh, this sounds big.
It is huge, a multi-decade, multi-billion-dollar international effort. Right now, as we speak, the Perseverance rover isn't just exploring and analyzing, it's actively collecting the most promising rock and soil samples it can find.
Choosing the best ones.
Exactly. It's specifically targeting those sedimentary layers within Jezero Crater, the ancient delta deposits, that scientists believe are most likely to preserve those subtle biosignatures we talked about. It's meticulously drilling core samples, sealing them in ultra-clean, robust sample tubes, and then strategically caching them, basically dropping them on the surface in designated depots for later pickup.
Like leaving messages in bottles for a future mission.
That's a perfect analogy. The plan, currently under development, involves a future series of missions. This is a complex, multi-step, incredibly ambitious international endeavor involving multiple spacecraft from NASA and the European Space Agency, ESA.
What's the plan?
The plan involves sending a lander to Mars, deploying a small fetch rover to precisely locate and retrieve these sealed tubes left by Perseverance, loading them into a small rocket called the Mars Ascent Vehicle.
A rocket launching from Mars.
Yes. Launching off the surface of Mars, a first carrying the samples into Mars orbit. Then another spacecraft, an Earth return orbiter, would rendezvous with the sample container in Mars orbit, capture it, seal it securely, and then fly all the way back to Earth, eventually landing the precious cargo safely in a specialized containment facility.
Wow. That sounds incredibly complex. like science fiction.
It is incredibly complex, pushing the boundaries of robotic technology, but the payoff could be immense. Analyzing these pristine samples, untouched by Earth's environment, not with a constrained rover on a distant planet, but right here in the most advanced, state-of-the-art laboratories we have on our planet, using every conceivable analytical technique at our disposal, techniques far too large or complex to send to Mars.
That's the key difference.
That is the key difference. This is considered our absolute best chance, perhaps our only chance in the foreseeable future, to definitively answer that fundamental question. Did life ever arise on Mars? It's our closest shot at getting empirical, undeniable proof one way or the other. It could be a complete game changer, potentially redefining our entire understanding of life's place in the universe.
It really puts Perseverance's current mission in perspective. It's not just exploring, it's collecting the evidence for perhaps the most important scientific investigation ever.
It truly is. It's laying the groundwork for that future breakthrough.
Okay, so Mars sample return is the big next step for Mars.
It absolutely is. Now, this whole discussion really raises an important, broader question, doesn't it? If life could have existed on Mars, a planet right next door in our own solar system, a world that clearly experienced periods of early habitability, well, what does that imply for the likelihood of life arising beyond our solar system, across the truly vast expanse of the galaxy?
Yeah, if it happened here twice, essentially.
Exactly. How do we even begin to estimate the likelihood of life elsewhere in our vast galaxy when the distances are just so immense and our direct observations are so limited compared to what we can do on Mars? That's where we really need to zoom out dramatically to a truly galactic scale.
All right, let's do that. From Mars to the Milky Way. Okay, that's a crucial pivot. So scaling up from the exciting, tangible prospects right here on Mars, let's talk about trying to take a kind of galactic census. How do we even begin to get our heads around the sheer scale and the probabilities involved in thinking about life, let alone intelligent civilizations, across the entire Milky Way galaxy? I mean, a galaxy holding hundreds of billions of stars? The numbers are just staggering.
They really are mind-boggling, feels almost impossible to grasp.
Right. Well, back in 1961, during a really seminal conference held at the Green Bank Observatory in West Virginia, a meeting focused specifically on the search for extraterrestrial intelligence, or SETI. A visionary astronomer named Frank Drake proposed a brilliant framework to structure this exact problem.
The Drake equation.
The Drake equation, exactly. And it's really important, I think, for listeners to understand this isn't some precise mathematical formula that spits out a definitive single number for how many aliens are out there.
No, it's not like NMCO quite. It's different.
Very different. Rather, it's a powerful probabilistic argument. It's a way to organize what we know, and perhaps more importantly, what we don't know about all the various factors that might be involved in the emergence of intelligent communicating life somewhere else in the galaxy.
It breaks down a huge, overwhelming question into smaller, slightly more manageable pieces.
Exactly. It truly gives us a mental scaffold, a way to structure our thinking and tackle this enormous, multifaceted question. And importantly, it forces us to confront our ignorance just as much as our knowledge. It highlights the gaps.
Precisely. The Drake equation is usually written as n equals r star times fp times net times phi times fc times l. Looks complicated maybe, but each term represents a specific question we need to ask.
Okay, let's break that down. What does each of those letters stand for?
Right. Let's go through each factor, drawing on what we think we know, and importantly, what we admit we don't, based on current science and the source material. Because each one of these terms is really a profound, scientific, and honestly, philosophical question in its own right.
Okay, lead us through it.
First up is N. This is the number we're ultimately trying to estimate. The number of civilizations currently residing in our Milky Way galaxy with which communication might be possible. Basically, how many technologically advanced societies are out there right now that we could potentially detect or talk to? That's the grand prize, the number everyone wants to know.
The big answer.
Next is R star. This represents the average rate of star formation suitable for the development of intelligent life within our galaxy.
How many new stars are born each year, basically?
Pretty much, yeah. And this is actually one of the factors we feel we know relatively well thanks to decades of modern astronomical observation across different wavelengths. Current estimates put it somewhere in the range of about 1.5 to 3 new stars forming per year in the Milky Way, on average.
Okay, so we have a steady supply of new potential homes.
A pretty solid starting point, yeah. It gives us a baseline rate for available real estate, if you like.
Got it. Next.
Then we have FP, which is the fraction of those newly formed stars that actually have planets orbiting them. Now, this was once a huge unknown, pure speculation back in Drake's time in 1961. We could only guess if planets were common or rare.
We couldn't see them back then.
Exactly. But now, thanks to incredible data pouring in from dedicated space telescopes like Kepler, and more recently, test missions designed specifically to hunt for exoplanets using the transit method.
Where they look for the little dip in starlight as a planet passes in front of its star.
Precisely. Thanks to those missions, we now have a much clearer picture. And the data is stunning. It strongly suggests that this number, FP, is actually very high. It's approaching 1.
Meaning most stars have planets.
Overwhelmingly, yes. It seems like planets are the rule, not the exception. The universe is teeming with planetary systems, far more common than we ever dared to imagine even just a few decades ago. So this term in the equation has seen a massive upgrade in our confidence level. It's likely close to 100%.
That's incredible. Okay, what's next after Feba?
Following that is NIA. This represents the average number of planets per star that has planets that can potentially support life. This is essentially trying to quantify the number of planets found within what we call the habitable zone, or that Goldilocks zone we discussed earlier.
Where liquid water could exist on the surface.
Exactly. The zone where temperatures are potentially just right. Now, estimates for this number are constantly improving as we discover more and more exoplanets and refine our understanding of what truly makes a planet habitable. It's not just about distance from the star. It involves factors like the planet's ooze, its atmosphere, does it have one, its geological activity, the stability of its orbit, the type of star it orbits.
So much more complicated than just being in the right place.
Much more complicated. But based on data from Kepler and other surveys, current estimates suggest that maybe, say, 1 in 5 sun-like stars might host an Earth-sized planet within its habitable zone. So we're getting much better at identifying these potential candidates, maybe billions of them in the galaxy, but refining this number, nay, is still a subject of intense study and debate. Defining habitability itself is tricky.
Okay, so NIA is getting clearer, but still uncertain. What comes after that? Because it feels like we're moving into even fuzzier territory now.
You're absolutely right. Here's where we hit some of the really big unknowns. The terms that truly dominate the uncertainty and expand the range of possible outcomes for N, the final number. First of these is LL.
LL.
Life, exactly. LL is the fraction of those suitable, potentially habitable planets, the near planets, on which life actually arises. This is a complete mystery, a monumental if.
The origin of life question.
The abiogenesis riddle, yes. Could life be an almost inevitable chemical outcome wherever the conditions are right? Like cosmic wet paint that always appears on a suitably primed, habitable canvas? If so, this fraction, FL, could be close to 1 or 100%.
Meaning life starts easily.
Relatively easily, yes, given the right ingredients and environment. OR is the origin of life from non-living matter, an extraordinarily rare event, a lottery win of cosmic proportions, involving such a complex sequence of improbable chemical steps that it's only happened once here on Earth and maybe nowhere else in our entire galaxy, or even the visible universe.
Wow, the range is huge.
The implications are absolutely staggering. If FLEL is infinitesimally small, then even with billions of habitable planets, we might be truly, profoundly alone, or at best, incredibly rare. If FLA is close to 1, then the Milky Way could be absolutely teeming with microbial life at the very least. We simply do not have the data to constrain this number yet. It's arguably the biggest unknown in the whole equation.
Okay, that's a big one. What's next?
Next up, assuming life has arisen, is phi. This is the fraction of those life-bearing planets on which intelligent life eventually evolves.
So going from microbes to, well, something that thinks.
Exactly. From slime to civilization, essentially. And again, this is another profound unknown. Is intelligence a common evolutionary outcome? Is it something that complexity naturally tends towards, given enough time and the right environmental pressures, maybe fluctuating climates, predator-prey relationships, the need for communication? Is it a beneficial adaptation that frequently emerges?
Or is it just a fluke that happened here?
Or is it a rare fluke? A unique evolutionary path taken by primates on Earth, driven by a specific sequence of environmental changes and genetic mutations that might not be easily replicated elsewhere. Perhaps intelligence like ours is even an evolutionary dead end in many cosmic scenarios. Maybe it leads to self-destruction, or isn't actually that advantageous long-term.
Deep questions about evolution itself.
Very deep questions about contingency versus convergence in evolution. If this fraction phi is very low, then even if the galaxy is filled with microbial life, if L is high, intelligent life capable of building telescopes or spaceships might still be exceedingly rare.
Okay, another huge uncertainty. We're piling them up here.
We are. Next comes FC. This is the fraction of those civilizations that develop intelligent life that then go on to develop a technology that releases detectable signs of their existence into space.
Detectable by us, you mean?
Detectable by us with our current or foreseeable technology. Primarily, historically, this meant things like radio waves or television broadcasts leaking into space, or maybe powerful, deliberate beacons, or even large-scale astroengineering projects. But just because intelligent life evolves doesn't automatically mean it will create radio telescopes or lasers aimed at the stars.
They might not be interested. Or use different tech.
Exactly. They might develop in entirely different directions, perhaps focusing inwards on mastering their own biology or consciousness. Perhaps their technology is purely biological or based on principles we don't understand. Maybe they communicate using methods we haven't even conceived of yet, neutrinos, gravitational waves, something else entirely. Our definition of detectable signs is often very Earth-centric, based on our own technological trajectory. So SC is another major unknown.
Right. And there's one more term.
L. Yes, the final factor, L. And this one is particularly sobering, I find. L represents the length of time, typically measured in years, for which such technologically advanced communicating civilizations release those detectable signals into space. How long does a civilization stay visible or audible across interstellar distances?
The lifespan of their detectable phase.
Precisely. A civilization might exist for millions, even billions of years, perhaps achieving incredible things, but it might only be detectable by our current methods for a relatively short period within that vast lifespan. Think about our own human history. We've only been broadcasting radio waves powerfully enough to leave the planet for a little over a century. That's a cosmic blink of an eye.
And what if civilizations don't last long after developing technology?
That's the dark thought bound up in L. What if they tend to self-destruct shortly after developing powerful technologies like nuclear weapons or uncontrolled AI? Or what if they simply move beyond radio, developing new, more advanced, perhaps more efficient or directed communication technologies like tight beam lasers or quantum communication that are no longer easily detectable omnidirectionally by distant, eavesdropping civilizations like ours? If L, the average communicative lifetime, is short, then even if many civilizations arise throughout galactic history, if the preceding terms are favorable, the chances of us overlapping in time with them being detectable might be very small. We might simply miss their brief window.
That L term really seems crucial and maybe quite pessimistic.
It carries a lot of weight and potentially a lot of pessimism, depending on your assumptions about civilizational longevity and technological evolution.
Okay, so we've gone through all the terms. R, FP, NA, FL, Phi, FC, L. A mix of things we know pretty well, things we're starting to get a handle on, and then these huge fundamental unknowns.
That's a perfect summary. The first few terms, related to stars and planets, have become much better constrained thanks to modern astronomy. The last few, related to the emergence and fate of life and intelligence, remain deeply uncertain.
So with all that uncertainty, especially in the later terms, what's the takeaway? Does the equation actually tell us anything?
Well, here's the fascinating part. Even if you plug in wildly conservative, some might even say pessimistic, estimates for those final, highly uncertain terms for FL, Phi, FC, and L. Let's say life is rare, intelligence is rare, technology is rarer still, and civilizations don't last long. It's still remarkably easy, because of the sheer scale of the first few terms, billions upon billions of potential habitable planets over galactic history, to arrive at a value for n, the number of currently detectable civilizations. That is far greater than 1. Maybe it's 10, maybe it's 100, maybe thousands. Even pessimistic estimates often suggest we shouldn't be alone right now.
So despite the unknowns, the math still points towards company.
The Drake equation, despite all its uncertainties, acts as a powerful argument. It strongly suggests that, based purely on the staggering number of stars and the now-known prevalence of planets, the Milky Way galaxy alone should be teeming with life, and quite possibly numerous intelligent civilizations throughout its history, and maybe even right now.
Wow. That powerful, almost intoxicating suggestion of a galaxy potentially filled with civilization.
That's a profound thought.
It is, but it slams headfirst into one of science's most profound and deeply unsettling mysteries. A mystery encapsulated in that deceptively simple, almost casual question posed by the physicist Enrico Fermi during a lunchtime chat almost 75 years ago.
Where is everybody?
Exactly. Where is everybody? That leads us straight into the Fermi Paradox. It's such a legendary anecdote in science, isn't it? 1950, Los Alamos National Laboratory. Enrico Fermi, This brilliant physicist, known for his sharp mind and back-of-the-envelope calculations, is having lunch with colleagues. They're chatting about flying saucers, the possibility of extraterrestrial life, how fast civilizations might travel between stars.
Just a casual lunch conversation for Nobel laureates.
Right. And apparently, amidst all this speculation, Fermi just looks up and asks simply, but where is everybody?
Such a simple question, but with such profound implications.
Exactly. That deceptively simple question, where is everybody, perfectly encapsulates what has become known as the Fermi Paradox, or, as it's sometimes more poetically and maybe more accurately called, the Great Silence. It's a question that has echoed down to the decades since, becoming a cornerstone of astrobiology and SETI, and a real challenge to our very assumptions about life's place in the universe.
And this is precisely the stark contradiction that lies at the very heart of the paradox. The Fermi paradox highlights the severe, glaring disparity between the high probability estimates for the existence of extraterrestrial civilizations, estimates derived from frameworks like the Drake equation we just discussed, which strongly suggest our galaxy should be teeming with intelligent life, potentially millions of civilizations over its history.
The optimistic conclusion from Drake.
Exactly. Between that optimistic conclusion and the utter, baffling, complete lack of any actual verifiable evidence for or contact with any such civilizations.
Zero evidence.
Zero credible, verifiable evidence. If the galaxy is indeed home to thousands or potentially millions of technological societies, and crucially, many of them would inevitably be millions, not billions of years older, and therefore presumably far more technologically advanced than our own fledgling civilization.
Capable of interstellar travel, maybe huge engineering projects.
One would assume so, given enough time and technological progress. So the question becomes, why, in all our searching, listening with radio telescopes, scanning the skies for optical signals, looking for anomalies around stars, why do we see absolutely no unambiguous signs of them?
Nothing.
Nothing definitive. No alien probes visiting our solar system, despite UFO reports, none have been scientifically verified. No gigantic stellar engineering projects, things like Dyson spheres built around stars to capture all their energy, which should be detectable by their waste heat signature. No clear, unambiguous artificial signals intercepted by our radio telescopes despite decades of searching. Just nothing. Only this great, vast, cosmic silence.
It's really eerie when you put it like that, an absence where we expect noise.
It is profoundly eerie. It's an absence in a universe that, by many statistical accounts, should be vibrant with activity. So where is everybody? That's the paradox.
How do scientists even try to resolve this? It seems like a massive contradiction.
Well, to grapple with this profound silence, scientists, philosophers, science fiction writers, lots of people have proposed various potential solutions or explanations. These are often conceptualized under the umbrella term of great filters.
Great filters. Sounds ominous.
It can be. The idea is that there might be one or more evolutionary or technological hurdles filters that are so incredibly difficult to overcome that they effectively prevent life from becoming widespread, technologically advanced, and, crucially for the paradox, detectable across the cosmos.
Like a bottleneck.
Exactly like a bottleneck. A stage in the development from simple life to galaxy-spanning civilization where nearly all attempts fail or get stuck or are eliminated. And the really critical question becomes, where is this filter located in the grand timeline? Is it in a distant past? Is it happening right now? Or is it, worryingly, still waiting for us in our future? The answer has incredibly different implications for humanity's own prospects.
Okay, let's explore some of these proposed solutions, these different ideas about where that great filter might actually be. One category of ideas, maybe the more optimistic one for us, or perhaps humbling, depending on how you look at it, is that the great filter is behind us. We've already passed it.
Meaning we're special somehow.
Essentially, yes. This hypothesis suggests that we are, in fact, incredibly rare. The filter wasn't a future challenge, but an incredibly difficult step that we managed to overcome while almost everyone else failed. The aha moment here isn't just that we're rare, but that our very existence, perhaps the initial improbable leap from non-life to the very first simple life, that crucial flea term in the Drake equation.
Abiogenesis being incredibly hard.
Exactly. Maybe that is the great filter. Maybe the spontaneous generation of life from non-living matter is so mind-bogglingly rare, involving such a precise and unlikely combination of chemicals and conditions, that it's only happened once, or maybe a handful of times, in the entire Milky Way galaxy.
Or maybe the filter was later.
Or maybe the filter was later, but still behind us. Perhaps the jump from simple single-celled organisms like bacteria to complex multicellular life with specialized tissues and organs was the incredibly hard step. Or maybe the evolution of large brains capable of abstract thought, tool use, and language, that phi term, is far more difficult and contingent on specific circumstances than we might imagine.
So something we achieved was the really hard part.
That's the idea. The implication here is that we have already passed the great filter simply by existing as a complex, intelligent, technological species. In this scenario, we might be one of the very first, perhaps even the only, intelligent civilization currently active in our entire galaxy. It makes us incredibly precious, incredibly unique, but also potentially profoundly alone, gazing out into a silent, empty universe.
It's a lonely thought, but maybe a hopeful one for our own future survival.
In a way, yes. But then there's a far more ominous possibility, one that should really give us a pause. The great filter is ahead of us.
This is the scary one.
This is the really scary one. This hypothesis suggests that it is perhaps somehow inherent in the nature of intelligent, technologically advancing civilizations that they eventually, maybe inevitably, destroy themselves before they can achieve widespread interstellar communication or colonization.
The filter is a future challenge we haven't faced yet.
Exactly. And maybe one that no one gets past. Think about it from our own perspective. The development of advanced technologies, while enabling incredible progress and understanding, often comes hand in hand with immense, potentially existential risks.
Like what?
Well, nuclear weapons are the classic example. Humanity has possessed the power of near-instant self-annihilation for decades now, and we've had some terrifyingly close calls.
The Cold War.
Absolutely. We're now grappling with the rapid rise of increasingly powerful and complex artificial intelligence. If that becomes uncontrollable or is poorly aligned with human values, some experts warn it could pose unforeseen existential dangers.
The AI takeover scenario.
Or just catastrophic misuse. Then there's the very real ongoing potential for catastrophic environmental damage through our own actions. Climate change, biodiversity loss, potentially pushing our planet's ecosystem past a point of no return, making complex civilization unsustainable.
Ruining our own nest.
Precisely. And you can imagine future possibilities too. Novel, engineered biological weapons getting out of control, maybe unforeseen consequences of nanotechnology. The list of potential self-inflicted filters is disturbingly long.
So in this view, L is short because civilizations crash and burn.
That's the grim implication. In this view, the lifetime of a communicating civilization, that L term in the Drake equation, is tragically short. Civilizations reach a certain level of technological power, and then through conflict, accident, or environmental collapse, they flicker out. The cosmic silence, then, isn't the sound of an empty universe. It's the sound of countless extinct civilizations. It's the graveyard of ambitions. It's a really sobering thought, isn't it? It forces us to look at our own current global challenges. Climate change, nuclear proliferation, AI safety, pandemics not just as serious problems, but as potential candidates for the great filter. Are we navigating one right now?
That really reframes our present moment.
It does. But okay, maybe it's not so binary. Either we're alone or we're doomed. There's a whole other category of potential solutions to the paradox, right? This idea that maybe they exist, but we cannot see them for some reason.
Right. This category contains a whole host of possibilities, and this is where speculation, some might say imagination, really takes off. It allows for a galaxy potentially teeming with advanced life while still explaining the silence we observe.
What are some of the main ideas here?
Well, one popular idea is that advanced civilizations might be deliberately hiding from us, or from everyone. Why? Maybe out of caution. This could be due to a sort of prime directive of non-interference, like you see in Star Trek, where they believe it's unethical to interfere with the natural development of less advanced species like ourselves.
The zoo hypothesis. We're being observed, but not contacted.
That's one flavor of it, yes. Or, perhaps more darkly, they might be hiding out of fear. Fear of cosmic predators. This leads to the dark forest hypothesis, popularized by the science fiction author Cixin Liu.
I've heard of that one. It's pretty chilling.
It is. It posits that the universe is actually a dangerous place, full of potential competitors or hostile entities. In such a universe, the safest survival strategy is to remain silent and hidden, because announcing your presence, broadcasting signals into the galaxy, is like shouting in a dark forest. It reveals your location to potential predators who might want to eliminate you before you become a threat. Silence, in this view, isn't absence. It's simply prudent survival strategy.
Okay, so maybe they're hiding. What else?
Another fascinating and maybe more profound thought is that they may have simply transcended, evolved beyond a physical form or a technological state that we could possibly recognize or detect with our current science.
Transcended. What does that even mean?
Well, it's highly speculative, of course, but what if advanced civilizations inevitably reach a point where they upload their consciousnesses into vast computational substrates, maybe living entirely within simulated realities, powered by planetary or even stellar-scale computers? They might exist as pure information or energy patterns,
Living in the Matrix, but on a cosmic scale.
something like that. Or perhaps they've moved beyond the need for physical planets altogether. Maybe they inhabit massive artificial constructs like those hypothetical Dyson spheres built around stars to capture nearly all their energy. Or maybe they exist as pure computronium, a theoretical arrangement of matter optimized for computation at the maximum possible density allowed by physics. If their existence is so fundamentally different from ours, so post-biological or post-physical,
Then our methods of searching, listening for radio, looking for planets like Earth would be completely irrelevant. We wouldn't even know what to look for.
exactly. We might be surrounded by intelligence, but in a form so alien it's literally invisible or incomprehensible to us.
That's a mind-bending idea. Are there more grounded explanations for why we might not see them?
Yes, there are simpler possibilities too. One is simply that we're looking for the wrong signals. Imagine, as the saying goes, trying to find email with a smoke signal.
Our technology is too primitive.
Maybe. We're primarily listening for radio waves, the technology we've only been using seriously for interstellar communication searches for, 60 years? And broadcasting powerfully for maybe a century. But what if radio is just a brief, primitive phase that advanced civilizations quickly move beyond?
Towards what?
Who knows? Maybe they communicate using highly focused laser beams, which we only detect if aimed directly at us. Maybe they use quantum entanglement for instantaneous communication across vast distances, something that wouldn't produce any detectable signal for us. Perhaps they modulate neutrinos or use gravitational waves in ways we can't yet decode. Or maybe they communicate via complex patterns embedded in the cosmic microwave background radiation itself. Our search methods might simply be too basic, too tied to our own limited technological experience, like an ancient civilization searching the skies for signal fires in an age of fiber optics.
We're listening on the wrong channel, essentially.
Or using the wrong receiver entirely. And finally, perhaps the simplest, though maybe least satisfying explanation is just the sheer mind-boggling vastness of space and time.
Distance is the filter.
Distance and time, yes. Even if civilizations are common, and even if they broadcast powerful signals for a long time, those signals travel only at the speed of light. The Milky Way galaxy is enormous, about 100,000 light-years across. A signal sent from a civilization on the other side of the galaxy would take 100,000 years to reach us.
We haven't been listening for very long.
Exactly. We've only been capable of detecting such signals for a tiny fraction of cosmic history. Our solar system, relatively speaking, is a tiny speck in a gargantuan volume of space. And our technological civilization is incredibly young. Perhaps signals are out there, crisscrossing the galaxy, but they simply haven't had enough time to reach our particular corner of the cosmos during the brief window we've been looking. Or maybe civilizations rise and fall, and we just happen to exist during a quiet period in our galactic neighborhood. Time and distance are immense filters in themselves, ensuring that only the closest or the longest lived or the most powerful communicating civilizations would have had a chance to make contact with us by now.
So a whole range of possibilities, from the profound to the practical, to explain the silence.
A huge range, and the truth might be a combination of several of these factors.
So what does this all mean for our actual search for life? Does the Fermi Paradox make it seem futile?
Not at all, I'd say. While the Fermi Paradox poses this profound challenge, this question that really makes you pause and think deeply about our place and our potential fate, it certainly hasn't stopped the scientific quest. If anything, it's fueled it. It's made us think more creatively.
How so?
It's pushed the scientific community to broaden the search beyond just listening passively for radio signals from Earth-like planets orbiting sun-like stars. We're now using more powerful tools than ever before, opening up entirely new frontiers and expanding our scope of where we look for life and what kinds of signs we look for.
Okay, so the search continues, maybe even more vigorously.
Absolutely, with new strategies and new targets.
Indeed. It seems like while the Fermi Paradox gives us this profound pause, this deep question mark, it certainly hasn't stopped the actual scientific quest. If anything, you're saying it's broadened our horizons.
Absolutely. It's compelled us to look in perhaps unexpected places, to think outside the box of just Earth-like life on Earth-like planets sending radio signals.
So we're expanding the search in incredible ways now, looking beyond just listening for those signals and even looking beyond Mars to other really compelling targets right here within our own cosmic neighborhood. Targets that offer entirely different, yet maybe equally exciting prospects for life.
Exactly. For example, some of the most exciting potential habitats for life in our solar system right now are considered to be the so-called ocean worlds, orbiting the giant planets in the outer solar system.
Ocean worlds, you mean like water planets out there?
Not quite planets, but moons. Think about Europa, which is one of Jupiter's large Galilean moons, and Enceladus, a much smaller but incredibly fascinating moon of Saturn.
Okay, Europa and Enceladus, what's special about them? They look like ice balls, don't they?
They do, on the surface. They aren't like Mars at all. They're covered in incredibly thick shells of water ice, probably kilometers, maybe even tens of kilometers deep, creating these desolate, frozen surfaces, colder than Mars even.
Does it sound very life-friendly?
On the surface, no. But, and again, there's a big, but the data we've gathered from spacecraft missions, particularly NASA's Galileo mission to Jupiter and the amazing Cassini mission to Saturn, strongly suggests that beneath these thick, insulating, icy crusts, both Europa and Enceladus harbor vast, globe-spanning oceans of liquid water.
Liquid water, under all that ice. How?
Tidal heating. As these moons orbit their massive parent planets, Jupiter and Saturn, they experience tremendous gravitational tugging and flexing. This constant stretching and squeezing generates friction and heat within their interiors, enough heat to maintain liquid water deep beneath the ice shell, even though they're far from the sun.
Wow, so internal heat keeps the oceans liquid. Are these big oceans?
Potentially enormous. Calculations suggest these subsurface oceans could hold significantly more liquid water than all of Earth's oceans combined. Europa's ocean is thought to be particularly vast and, crucially, likely in direct contact with a rocky silicate seafloor beneath it.
Why is contact with rock important?
Because that allows for potential water-rock interactions, chemical reactions that could release energy and nutrients into the ocean, essential ingredients for life. Think about hydrothermal vents on Earth's ocean floor.
Right, you mentioned those earlier.
Exactly. And Enceladus. Enceladus is particularly tantalizing. It's a real star right now in astrobiology. Because Cassini didn't just infer an ocean, it actually observed Enceladus actively spewing enormous plumes of water vapor and ice particles, along with other materials, directly into space from giant cracks nicknamed tiger stripes near its south pole.
It's spraying its ocean out into space.
It seems to be doing just that. Think about it. A moon actively venting its subsurface ocean directly into space through cracks in its ice shell. It's essentially offering us a free sample. We don't even necessarily need to drill through the ice. We could potentially fly a spacecraft through those plumes and analyze their composition directly.
That's incredible. What did Cassini find in the plumes?
Cassini flew through the plumes multiple times, and its instruments detected not just water ice, but also salts, like sodium chloride, basically table salt, suggesting the ocean is salty like Earth's. Silica nanoparticles, which strongly hint at ongoing high-temperature hydrothermal activity on the seafloor below, maybe 90 degrees Celsius or more, and a rich cocktail of complex organic molecules, including methane, ammonia, carbon dioxide, and even molecular hydrogen.
Hydrogen. Why is that significant?
Molecular hydrogen is potential food. On Earth, many microbes living in environments without sunlight, like around hydrothermal vents, use hydrogen as a source of chemical energy to fuel their metabolism. Finding hydrogen in the plumes suggests Enceladus's ocean might have the chemical energy needed to support life.
So Enceladus seems to have liquid water, organic molecules, and an energy source, the key ingredients.
Pretty much the trifecta for life as we know it, all potentially present in an environment shielded from surface radiation by that thick ice shell. This makes Europa, with its vast ocean and potential rock contact, and especially Enceladus, with its confirmed plumes, organics, and likely hydrothermal vents, absolute top priority targets for future astrobiology missions.
Are there missions planned?
Yes. NASA's Europa Clipper mission is scheduled to launch soon, designed to make dozens of close flybys of Europa, mapping its ice shell, confirming the ocean's presence and characteristics, and searching for potential plume activity. And there are concepts being developed for future missions to land on Europa, or perhaps fly through Enceladus's plumes with even more capable instruments, specifically designed to search for biosignatures. These ocean worlds represent a completely different potential path for life in our solar system, separate from Mars.
Fascinating. So we're looking underground on Mars and under the ice on these outer moons. What about looking even further afield outside our solar system entirely.
Right. And that's where another revolutionary tool comes into play. Moving beyond our solar system to those thousands of exoplanets we now know exist orbiting distant stars, the James Webb Space Telescope, or JWST, represents a truly monumental leap forward in our ability to search for signs of life.
JWST. We hear a lot about its amazing images. How does it help find life?
Its capabilities for studying exoplanet atmospheres are absolutely groundbreaking. It's fundamentally changing how we approach exoplanet characterization and the search for biosignatures beyond our solar system. JWST primarily uses a technique called transit spectroscopy.
Okay, spectroscopy is analyzing light, right?
Mhm.
How does transit spectroscopy work?
Exactly. So remember how telescopes like Kepler and TESS find planets by looking for the dip in starlight when a planet transits or passes in front of its host star from our perspective?
Yeah, the mini eclipse.
Well, JWST can take that a crucial step further. When that transit happens, a tiny fraction of the starlight actually filters through the upper layers of the exoplanet's atmosphere, if it has one, on its way to the telescope.
Ah, the light goes through the air around the planet.
Precisely. As that starlight passes through, the unique chemical composition of the gases in that atmosphere will absorb specific wavelengths, specific colors of light. Different gases absorb different characteristic wavelengths, so the atmosphere leaves a unique chemical fingerprint or spectral signature imprinted on the starlight that reaches JWST.
Like a barcode for the atmosphere's ingredients.
That's a perfect analogy, a chemical barcode. By meticulously capturing the star's light during a transit, spreading it out into its full spectrum like a rainbow, and comparing it to the star's light when the planet isn't transiting, JWST can identify which wavelengths are missing, which ones were absorbed by the planet's atmosphere.
And that tells us what gases are there.
Exactly. By analyzing these incredibly subtle absorption features in the filtered light patterns, JWST can actually determine the chemical composition of that distant exoplanet's atmosphere, what gases are present, like water vapor, carbon dioxide, methane, oxygen, ozone, and potentially even in what rough concentrations.
What's it looking for specifically in terms of finding life?
What it's specifically looking for are combinations of what we call biosignature gases that, especially if found together, might strongly suggest the presence of biological processes. Common targets include things like oxygen, ozone, which is produced from oxygen, methane, and water vapor.
Why those gases?
Individually, these gases can sometimes have purely geological or photochemical origins. For example, significant oxygen could, in some scenarios, build up in an atmosphere just from intense ultraviolet light from the star breaking down water molecules without any life involved. Methane, as we discussed with Mars and Enceladus, can definitely be produced geologically.
So finding just one isn't proof.
Not usually, no, but if we find certain gases in combination, particularly gases that shouldn't naturally coexist in large quantities because they tend to react with each other chemically, like finding abundant oxygen and abundant methane in the same atmosphere simultaneously.
They should destroy each other.
Over geological timescales, yes, they should react and reach a stable, low-level equilibrium. Finding them both together in large amounts suggests a state of chemical disequilibrium. It implies that some active process must be constantly producing and replenishing both gases at a high rate to keep them abundant.
And that process could be life.
That process could very well be life. On Earth, the high levels of both oxygen from photosynthesis and methane from microbes coexisting in our atmosphere are a direct consequence of biological activity. It's a planet-scale signature of a living biosphere actively modifying its atmosphere. Discovering such a dynamic, unbalanced mix of gases on an exoplanet, especially within its star's habitable zone, would be incredibly difficult to explain by geology or photochemistry alone.
That would be the smoking gun.
It would be perhaps the strongest evidence we could get remotely for the existence of a living, breathing world actively cycling elements like carbon and oxygen through its biosphere. This capability of JWST to potentially detect the atmospheric fingerprints of life on rocky worlds orbiting other stars is fundamentally changing the game.
So we're moving from just finding planets to actually sniffing their air for signs of life.
That's a great way to put it. For the first time in history, we have the technological means to start assessing not just the potential habitability, but maybe even detecting the direct atmospheric consequences of life on worlds light years away, a capability that was, frankly, pure science fiction just a decade or two ago.
It really feels like we're entering a new era in this search.
We absolutely are. Between the upcoming Mars sample return, the exploration of ocean worlds like Europa and Enceladus, and the atmospheric characterization of exoplanets with JWST, we have multiple powerful avenues opening up simultaneously.
Wow. Okay, so from the ancient, dried-up river deltas of Mars, potentially holding clues to past life, to the deep, dark, icy oceans of distant moons within our own solar system, hinting at hidden hydrothermal vents and maybe life independent of sunlight, and finally, all the way out to sniffing the atmospheric fingerprints of exoplanets hundreds or thousands of light years away. Our journey today has covered some truly immense cosmic ground. We've used incredible ingenuity, followed the scientific evidence, and faced some profound questions. But what does it all boil down to? Where does this leave us?
That's the big question to wrap up with, isn't it? Hashtag tag outro. So yeah, what does this all mean for us standing here on Earth looking out? I think we stand at a truly remarkable crossroads in this grand millennial-old quest to understand if we're alone.
It certainly feels like a pivotal moment.
It really does. We're armed with these unprecedented tools, rovers digging on Mars, spacecraft plumbing the depths of icy moons, telescopes tasting the air of alien worlds, tools that are finally allowing us to gather meaningful empirical data on these fundamental questions about life beyond Earth.
Moving beyond just theory.
Exactly. Mars presents us with this fascinating, desiccated world that we know was once warm, wet, and potentially habitable, holding the tantalizing possibility of preserved biosignatures just waiting beneath the dust, waiting for us to bring them back and definitively discover them.
The promise of sample return.
The huge promise of sample return. Then the Drake equation, for all its inherent unknowns, still provides us with this compelling, logical, probabilistic framework, powerfully suggesting that the galaxy should be rich with life, based on the sheer numbers.
The statistics seem favorable.
They do, yet the Fermi Paradox immediately confronts us with that profound and eerie silence, challenging our optimistic assumptions and forcing us to consider truly humbling or perhaps even terrifying explanations for that apparent absence of cosmic neighbors.
The great silence is hard to ignore.
It really is. And now we have these new frontiers, the ocean worlds, hinting at life powered by chemistry, not sunlight, and exoplanet atmospheres where we might soon detect the breath of an alien biosphere. So whether we ultimately find that life is common and abundant across the cosmos, popping up wherever conditions allow, or whether we discover that we are, in fact, a unique and incredibly precious anomaly in a largely sterile universe.
Either answer is profound.
Either answer will forever reshape our understanding of our own existence, our significance, our place in the grand cosmic narrative. This truly is, I believe, a golden age of exploration, where the answers to these age-old questions are no longer purely philosophical speculations, but seem to be increasingly within the grasp of rigorous scientific inquiry.
It's an amazing time to be pondering these questions. The great silence, as you say, is still a mystery. It echoes through the cosmos, and for now, the search continues, more powerfully than ever. But as you, our listener, reflect on this deep dive, think about the Drake equation, the Fermi Paradox, the potential great filters. And maybe consider this, especially that idea of the filter being ahead of us.
The sobering possibility.
The most sobering one.
Right.
If there's even a chance that the great filter truly is ahead of us, that most, or maybe all, advanced technological civilizations eventually extinguish themselves through war or environmental collapse or unchecked technology, well, consider this. What profound responsibility does that place on us, on humanity, as a currently young, maybe naive technological civilization? What does it demand of us to ensure we navigate our own challenges, that we don't become just another silent echo in the cosmos, just another data point proving the filter exists? What does it mean for us to manage these existential risks, to cooperate, to ensure the long-term survival of intelligent life, perhaps not just for ourselves, but as potential representatives of intelligence for this entire sector of the galaxy?
It adds a whole new weight to our current decisions.
It really does. Something profound to ponder. Thank you for joining us on The Deep Dive.